Hello, everyone. So last time we left off with the description of how we can examine heat transfer through the conduction of simple materials. One of the things we have to watch out for is it turns out that most materials aren't quite so simple. So we often find a lot of composite materials, whether they're wood or whether it's something simple like a pipe with several different layers of insulation. Say there may be a tape layer, a thermal insulating layer, an electrical insulating layer, and an outside coating. These are fairly common, and these range anywhere from the walls of reactors to the pipes we're examining. So one of the tricks that we have to figure out is how I can examine how heat transfers from, say, the inside of a hot reactor to the cold outside of the atmosphere if I'm going through, say, three different materials. So one of the ways we could go ahead and try and solve this is to solve for each component. If I know the inside temperature and the temperature at the interface in between the walls, I can simply use Fourier's law to determine the heat flux going through the material. And then based on uh, based on the steady state principle, we can assume that we'd have a similar heat flow going through the other two. But let's be honest, this gets a little bit messy as I'd have to figure out what the temperature is at the interface. So I might need a little bit a simpler method. So again, one of the things that we're going to make use of is that the temp should drop predictably across the composite material because of that constant heat flow. So if I have some way to determine the heat flow going from the inside to the outside, I should be able to back solve for T1 and T2, which might be a better way of doing that. So one of the tricks that we can end up pulling is trying to figure out a net parameter to describe this whole composite material together. And it turns out the trick that we're going to be doing is generating a coefficient that contains the size and the and the conductivity constant for each of the submaterials and then adding them up. Now, one of the real tricks you have to watch out for is instead of adding them up as K1 over B1, like we originally had the equation, we instead have to add them all up in a single denominator. And the K1 moves from being up here to being the denominator of the length. But what ends up happening is that we can end up adding these ratios of size and conductivity together to give a net parameter that describes how conductive the material is. And so what this allows us to do is, as long as I know the composition of the material, I can determine the predictable heat flux across the entire material, and then I can help use this to figure out things like intermediate temperatures, as well as design composite materials, which can functions as insulators for complex systems. So this is essentially going to be our modified Fourier's equation, which we're going to be using quite regularly, as it is more general and much more descriptive than the simple Fourier's equation we used last time. But let's go ahead and try and put this to use to a real world problem. So let's say I'm having a reaction that takes place essentially at a furnace level. Let's say I'm doing something like purifying metals or ores. So this might take place at a fairly reasonable temperature of 700 degrees C. As chemists, we don't think of this as reasonable, but this is not uncommon for a lot of materials processes. So I'm going to go ahead and do this essentially in a brick kiln that's made of 3 different layers. So my inside layer is going to be 30 centimeters of fire brick. So this is actually a fairly common technique that you'll see in even a lot of fireplaces. However, to give it increased rigidity, we often need a thick steel plate. So this is essentially the portion that gives the real framing and solidity to the material and helps prevent any permeation of uh, that helps prevent any permeation of reactants or dust outside of the fire brick. So you'll see this in a lot of fireplaces. However, we also need an additional set of insulation because it turns out fire brick is a good insulator, but often not good enough. So you may have a nice layer of rock wool exterior coating the surface. So you'll see this fairly commonly in a lot of fireplaces or kilns. So now what I need to try and do is, assuming that I get the temperature down to something that's just reasonably hot and not deadly, let's assume the exterior temp is about 50 degrees C. I can deal with 50 degrees C. Might be a nice place to warm my hands. Don't keep it there too long. That's about the temperature at which meat cooks. So using this, I need to try and determine what's the heat flux, or essentially how much heat is my fire losing, say, per area of furnace. So let's go ahead and do our classic trick. When in doubt, diagram it out. It's a really helpful way to try and visualize the system. So I have my fire brick near the inside. This should be fairly warm. My thin steel coating and my rock wool exterior coating. So I can go ahead and take the K and B parameters for each one, plug them into my equation. I have my temperature drop, so this should end up giving me a net negative flux because I am losing heat from the system. That's good. And we end up, turns out we end up losing about 140 watts per square meter of furnace area. So again, this is going to be about 140 joules per second. So this is a fairly decent heat loss, but not huge. And then what we can do is use our simple Fourier's equation to back solve for T1 and T2, because now I know the heat flux, and you can say solve for this balance to get you T1, and then either solve a second balance to get T2, or start with this one, start with the outside temperature and work your way in to get T2. Either way, it's not too bad. And it turns out when you do this, it turns out that T1 and T2 are almost the exact same temperature of 266.8. So degrees C, or about 500 degrees Kelvin. So a little bit closer to the outside temperature, but it's a good thing we added on that extra layer of rock wool. Otherwise, well, boiling water would be a little bit of an understatement. So what we can do is use all of these values to try and help us figure out which layers are best insulator. So when we go through this, it should be fairly easy to see that my thin metal layer, while it provides structural advantages, doesn't actually do me much good for insulation because I have a small number divided by a big number. So this term pretty much drops out in terms of how much it helps the insulation. But these two terms are actually going to be a lot more important. So I have my much better insulating value for the rock wool. It's about twice as good of an insulator as my fire brick. But one of the things you might make note of is it's also 5 times as thin. Because what we want if we have a good insulator is we want this term down here to be as large as possible. And we get that by having a thick material with a small coefficient. So what ends up happening here is because the thickness of the fire brick becomes more important than its actually insulating property, a lot of the insulation, most of the insulation is being provided by the fire brick, but a fair bit of insulation is actually being portrayed by the rock wool. And you can actually see this with the temperature change as well. Most of the decrease in temperature happens in the fire brick phase, but we still drop almost over 200 degrees Celsius when we go from T2 to the outside. So again, still very good thing we added the asbestos or the rock wool. So again, trying to be able to get an idea both in terms of the concepts as what's happening, as well as kind of the mathematical importance of these terms. And so if you're in a hurry, one of the things you can always try and do is figure out which terms will reasonably drop out. But again, using these basic principles and say some of the ones we've determined last time, like how you can translate composite materials to a steel pipe, you can actually solve a lot of simple heat transfer systems. However, one of the things we have yet to talk about is what sort of influence we might have of how the temperature moves from the surface of my insulator to the outside system. Because some insulation is almost always provided by the substance we're translating heat from and to. So next time, we'll be talking about how we need to account a little bit for convection and not just conduction. Till then, take care.